You need to understand something about Ernest Shackleton before we go any further. In 1914, when his ship Endurance became trapped in the pack ice of the Weddell Sea, he didn't panic. He didn't rage against fate or curse the Antarctic gods. Instead, he organized soccer matches on the ice. He held singing competitions. He made his men feel, even as their wooden vessel was being slowly crushed by the pressure of a frozen ocean, that they were part of something manageable, something human. This is the kind of person who goes to Antarctica. Not the reckless adventurer of popular imagination, but someone who understands that survival in extreme environments is mostly about routine, about creating normalcy where none should exist. But Shackleton never crossed what we now call the Ross Ice Shelf in its entirety. That distinction belongs to a man whose name you probably don't know, and whose journey reveals something far stranger about the nature of Antarctic exploration than any dramatic rescue or heroic failure. His name was aptly Cherry Garrard, and while he's remembered, when he's remembered at all, for participating in Robert Falcon Scott's doomed expedition to the South Pole, his real contribution to history happened in the winter of 1911, during what he would later call the worst journey in the world. You have to picture the setup carefully. The Terra Nova expedition had established its base camp at Cape Evans on Ross Island in January 1911. Scott's plan was to spend the Antarctic winter preparing for the push to the pole the following spring. But there was a problem, a scientific problem that had been nagging at expedition zoologist Edward Wilson for years. Emperor penguins, those peculiar birds that seem to exist in defiance of every reasonable biological principle, bred in the middle of the Antarctic winter. No one had ever collected their eggs during this period. Wilson believed, incorrectly as it turned out, but with the certainty of Edwardian science, that studying emperor penguin embryos might provide the missing link in understanding the evolution of birds from reptiles. So in June 1911, in the middle of the Antarctic winter, when temperatures regularly dropped below -60 degrees Fahrenheit, when the sun didn't rise at all, Cherry Garrard, Wilson, and Henry Birdie Bowers set out to walk 67 miles across the Ross Ice Shelf to the Emperor Penguin Rookery at Cape Crozier. They would be pulling sledges weighing over 700 pounds. They would be walking in complete darkness. And they would be doing it in weather so cold that their teeth cracked when they breathed. Their sleeping bags froze solid and took hours of body heat to thaw each night. And their tent once blew away in a storm, leaving them huddled in a stone hut they'd built, certain they would die. The journey took 5 weeks. 5 weeks of walking through a landscape that you cannot properly imagine unless you've been there. And even then, the human mind struggles with it. Antarctica in winter isn't just cold. Cold is something you can dress for, something you can manage with enough layers and enough movement. Antarctica in winter is a kind of absolute. It's the negation of warmth, the absence of comfort, the place where your body's heat is constantly being stolen by air so frigid it seems to have malicious intent. Cherry Garrard described how their breath would freeze into ice on their balaclavas, then melt from their body heat, then freeze again, creating masks of ice that cut their faces. He described how they couldn't wipe the sweat from their bodies during the day. So it froze in their clothes, adding pounds of ice to their already unbearable loads. But here's what history overlooks, what makes this story relevant to understanding Antarctic exploration in general. They weren't walking across solid ground. The Ross Ice Shelf is a floating platform of ice, hundreds of feet thick in places, that covers an area roughly the size of France. It moves. Slowly, imperceptibly to human senses in the short term, but it moves, flowing toward the sea at a rate of several feet per day. Cracking, reforming, creating crevasses that can swallow a man and his sledge without warning. When Cherry Garrard and his companions walked across it in total darkness, navigating by compass and dead reckoning, they were walking across what was essentially a frozen ocean, held together by cold alone. And they succeeded. They reached Cape Crozier. They found the penguin rookery. They collected 5 emperor penguin eggs. Then, on the return journey, a blizzard destroyed their tent and nearly killed them all. They survived by crawling into the stone igloo they'd built on the outward journey and waiting in complete darkness for the storm to pass. They had no tent, no real shelter, and no certainty that they would live. Bowers, with characteristic British understatement, spent the time reciting poetry. Cherry Garrard, with characteristic honesty, admitted he spent it wondering if freezing to death would hurt. When they finally made it back to Cape Evans, weighing less than they'd started, their sleeping bags solid blocks of ice, their faces scarred from frostbite, Scott's first question was whether they'd gotten the eggs. They had. Wilson immediately began preserving them for transport back to England. The scientific establishment, when they finally received these eggs after Scott's death, studied them briefly and determined that they showed nothing particularly interesting about the evolution of birds. The worst journey in the world had been, from a scientific standpoint, essentially pointless. But you need to understand what they'd actually done, what they'd actually crossed. Because the Ross Ice Shelf, that massive platform of ice, wasn't just a geological feature. It was a barrier, not metaphorical, but actual. For decades, explorers had believed that Antarctica was surrounded by an insurmountable wall of ice, a barrier that marked the edge of the navigable world. James Cook, during his circumnavigation of the Antarctic region in the 1770s, had encountered what he called ice hills that extended as far as the eye could see. He'd concluded that if land lay beyond this barrier, it was inaccessible, doomed by nature to perpetual frigidness and never once to feel the warmth of the sun's rays. The Ross Ice Shelf was part of this barrier. When James Clark Ross discovered it in 1841, he called it the Victoria Barrier, and he described it in terms that made it sound like the edge of the world. A perpendicular cliff of ice between 150 and 200 feet above the level of the sea, perfectly flat and level at the top, and without any fissures or promontories on its even seaward face. He followed this cliff for 250 miles without finding any way through it or over it. So, when Cherry Garrard and his companions walked across the top of this barrier in 1911, they weren't just going on a penguin egg hunt. They were crossing what previous generations of explorers had considered an absolute limit, the place where the known world ended. And what did they find on the other side of this ice wall? Not a hidden land, not a secret warm valley, not any of the fantastical geographies that 19th century theorists had imagined might exist at the poles. They found more ice. They found penguins that had adapted to breed in conditions that should have been impossible for any warm-blooded creature. They found a landscape so hostile, so inimical to life, that simply surviving there for 5 weeks was an achievement that pushed human endurance to its absolute limit. But here's where the story becomes more complex, more interesting than just a tale of survival. Because Cherry Garrard's journey wasn't the first time someone had crossed this barrier. And it wouldn't be the last. And each time someone crossed it, they found something different on the other side. Not because the landscape changed, but because what we look for shapes what we see. The first crossing of the Ross Ice Shelf, the first journey across this wall of ice into the interior of Antarctica, happened in 1902. You might know the name, Robert Falcon Scott, the same Scott who would later die returning from the South Pole, led a sledging expedition from his ship Discovery across the ice shelf and onto the polar plateau beyond. He took with him Ernest Shackleton. Yes, the same Shackleton who would later lead that famous survival story. And Edward Wilson. The same Wilson who would convince Cherry Garrard to go penguin egg hunting 9 years later. This first journey across the barrier is worth examining in detail because it established patterns that would repeat throughout Antarctic exploration. Patterns of expectation and disappointment, of scientific hope and practical reality. Scott, Shackleton, and Wilson weren't just exploring. They were testing theories. Victorian and Edwardian science had made predictions about what lay beyond the ice wall. Some geographers believed that Antarctica was merely a ring of ice surrounding an open polar sea. Others thought there might be an ice-free continent, warmed by volcanic activity. Still others speculated about the possibility of life forms that had adapted to extreme cold, perhaps even human populations that had developed in isolation. None of these theories proved correct. What Scott, Shackleton, and Wilson found beyond the ice wall was more ice, and cold, and scurvy, though they didn't recognize it at first. They made it 82 degrees south, farther than anyone had ever been, and they nearly died doing it. Shackleton became so ill that Scott sent him home in disgrace, believing he'd shown weakness. The relationship between the two men never recovered. But more importantly, they'd crossed the barrier, and the crossing revealed that Antarctica wasn't hiding anything. It was exactly what it appeared to be, the coldest, driest, most inhospitable place on Earth. Yet people kept crossing that barrier, kept pushing beyond the ice wall. Why? When you lie in bed tonight, comfortable and warm, you might wonder about this question. What drives people to go to places that offer nothing but suffering and danger? The easy answer is glory, or scientific advancement, or national pride. These motivations were certainly present. But if you read the diaries and letters of the men who actually made these journeys, you find something more complicated, more human, and more boring in its way than tales of daring do would suggest. What emerges from these accounts is that many Antarctic explorers were driven by something far more mundane than heroism. They were driven by routine, by the simple need to see what lay beyond the horizon, by professional obligation, by the desire to justify the expense of their expeditions, and often by the fact that they'd already come so far that turning back seemed more difficult than pressing forward. Cherry Garrard, describing his winter journey to Cape Crozier, admitted that there were moments when he would have gladly given up. But the social obligation to his companions, the simple human unwillingness to be the one who quit, kept him moving. This might seem anticlimactic, but it's historically significant. Because the crossing of Antarctica's ice wall, the gradual, painful penetration of the continent's interior, wasn't accomplished by superhumans. It was accomplished by ordinary people doing an extraordinary job of maintaining routine in impossible circumstances. They got up every day, they ate their rations, they broke camp, they pulled their sledges, they made camp again, they ate again, they slept, and they repeated the process day after day, even when every sensory input told them that what they were doing was insane. And what did they find on the other side of the ice wall? After all these crossings, after decades of exploration, here's where you need to pay attention, because this is where history takes an unexpected turn. The answer they found was geological, yes, but it was also deeply philosophical. What lay beyond Antarctica's ice wall was evidence of a world that no longer existed. When expeditions finally penetrated deep enough into the continent, when geologists finally examined the rocks exposed in the Transantarctic mountains, they found fossils. Not just any fossils, but fossils of plants and animals that could only have lived in temperate or even subtropical climates. They found coal seams, evidence of vast forests. They found fossils of reptiles similar to those found in Africa, South America, and India. These discoveries, accumulated over decades of expeditions that pushed beyond the ice barrier, led to the theory of continental drift, later refined into plate tectonics. Antarctica, this frozen wasteland, this place that seemed to represent the very edge of habitability, turned out to be a keystone in understanding Earth's history. It was proof that continents moved, that the planet's surface was not fixed, that the world of today bore little resemblance to the world of 200 million years ago. But this knowledge came slowly, painfully slowly. The first fossils were found by Scott's party on their return from the pole in 1912. They were carrying 35 pounds of rock samples when they died, specimens they refused to abandon even as they froze and starved. These rocks, found with their bodies 8 months later, included fossil plants that provided early evidence for Antarctica's warm past. Was carrying those rocks, maintaining scientific procedure even in the face of death, a rational decision? Or was it simply what they'd trained themselves to do? The routine they couldn't break, even when breaking it might have saved their lives. You might consider this question as you drift toward sleep tonight. This question about the weight we carry and why we refuse to put it down, even when the burden becomes unbearable. The crossing of Antarctica's ice wall, then, reveals something unexpected. The explorers who penetrated this barrier found not a hidden world, but evidence of worlds long past, evidence that nothing is permanent, that even ice has a history, that barriers eventually fall, though not in the ways we expect. But there were other crossings that took different forms, that revealed different things about what lies beyond the limits we perceive. You need to know about Marie Tharp before we continue, though her name rarely appears in the same breath as the Antarctic explorers we've been discussing. This is partially because she never went to Antarctica. She never went on any ocean expedition at all, in fact, despite spending her entire career studying the ocean floor. And it's partially because she was a woman working in geology in the 1950s, which meant she was prohibited from joining research vessels. But mostly it's because what she discovered beyond the ice wall wasn't a place you could walk to. It was a place that existed beneath everything, hidden under miles of water and ice. A landscape no human had ever seen, but which was more vast and geologically significant than Antarctica itself. Marie Tharp started working at Columbia University's Lamont Geological Observatory in 1948. Her job, initially, was to draft and plot data, specifically to take the echo soundings that research vessels collected from the ocean floor and turn them into meaningful cross-sections and maps. This was considered women's work, the tedious but necessary task of converting numbers into pictures. The men did the interesting science, the interpretation, the theorizing. The women did the drafting. But you need to understand what these echo soundings represented. During and after World War II, naval vessels had begun systematically mapping the ocean floor using sonar. Ships would emit sound pulses downward and measure how long it took for the echo to return, calculating water depth from the time delay. This produced profiles, cross-sections showing the shape of the ocean bottom along a ship's track. Before this technology, the ocean floor was largely unknown. A few scattered depth measurements existed, taken by ships lowering weighted lines. But these were so sparse and so time-consuming that most nautical charts simply marked vast areas of ocean as depths unknown. The Antarctic region, in particular, was almost completely unmapped. The ice wall that Ross had encountered, that Cherry Garrard had crossed, was only the visible portion of Antarctica's barrier. Beneath the water surrounding the continent lay another wall, a continental shelf that dropped away to abyssal depths. And beyond that, No one knew. The assumption, based on the limited data available, was that the ocean floor was relatively flat and featureless, perhaps tilted slightly, but essentially a vast plain of mud gradually accumulating sediment. Marie Tharp's job was to plot the profiles from the Atlantic Ocean first. She worked with Bruce Heezen, a geologist who went on the research cruises and collected the data. Heezen would return with boxes of echo-sounding records, long scrolls of paper showing the seafloor's profile as a continuous line. Tharp would plot these profiles at an exaggerated vertical scale to make features more visible. Then she would try to correlate features across different ship tracks, building up a three-dimensional picture of what the ocean floor looked like. What she found, within the first year of this work, was something that shouldn't have been there. Running down the middle of the Atlantic Ocean, roughly equidistant from the continents on either side, was a valley. Not a small valley, but a rift comparable in size to the Great Rift Valley in Africa. It was flanked by mountains, underwater mountains that rose thousands of feet from the abyssal plain but never quite broke the surface. And this rift valley extended, as far as the data showed, the entire length of the Atlantic Ocean. When Tharp showed this finding to Heezen, he dismissed it. He told her it was girl talk, that she must have made an error in her plotting. The reason for his skepticism was simple. A rift valley in the middle of the ocean was exactly what you'd expect to see if continents were drifting apart. If new ocean floor was being created at the center of the ocean and pushing outward. But continental drift, though it had been proposed by Alfred Wegener in 1912, was still considered a fringe theory in the 1950s. Most geologists believed continents were fixed, that they might rise or fall slightly due to erosion or sediment deposition, but that they certainly didn't wander around the globe like ships on an ocean. So Tharp went back to her drafting table and checked her work. She plotted the profiles again. She looked for errors in the data. She found none. The Rift Valley was real. And as more data came in from additional cruises, she found that it wasn't just in the Atlantic. The Rift Valley continued around the southern tip of Africa and into the Indian Ocean. It extended toward Australia. Wherever there was enough data to map the ocean floor in detail, the rift appeared. But here's where the connection to Antarctica becomes crucial. Because the Rift Valley, this submarine feature that Tharp had discovered, didn't just run through the Atlantic and Indian Oceans. It encircled Antarctica. The mid-ocean ridge system, as it came to be called, formed a continuous underwater mountain range that wrapped around the entire planet. And Antarctica sat in the middle of it like a keystone, like a pivot point around which the whole system organized itself. This wasn't immediately obvious. The Antarctic waters were the least explored, the most dangerous for research vessels. Ice made sonar mapping difficult. Storms in the Southern Ocean were legendary. Waves could reach 80 feet, winds could strip paint from metal, and temperatures could freeze spray into ice on a ship's superstructure, making vessels top-heavy and prone to capsizing. So the data came in slowly, one cruise at a time, each ship pushing a little farther south, each new track revealing a little more of the picture. Tharp worked on this mapping project for the better part of 2 decades. She plotted millions of individual depth soundings. She created cross-sections showing the ocean floor's profile every few hundred miles. And gradually, she assembled what no one had ever seen before. A complete picture of the ocean floor. A landscape that covered more than 2/3 of the Earth's surface, but had been completely hidden from view. What did this landscape look like? You should try to picture it, because it's relevant to understanding what the Antarctic ice wall really is. Imagine the continents are islands, floating in an ocean that's been drained away. The continental shelves, the shallow areas around each continent, drop away at a relatively steep slope, falling from a depth of about 600 feet to depths of 12,000 feet or more. These are the true edges of the continents, the boundaries between continental crust and oceanic crust. Beyond the continental slope lies the abyssal plain, vast stretches of relatively flat seafloor covered in sediment. And rising from this plain, like a mountain range that's been split down its center and pulled apart, is the mid-ocean ridge system, the rift valley that Tharp had discovered. Antarctica, in this drained ocean view, looks different than it does on a standard map. It's not just a continent sitting at the bottom of the world. It's a continent surrounded by and partially covered by ice, sitting on the Antarctic plate, which is slowly being pushed and shaped by the spreading ocean floor around it. The Ross Ice Shelf, the Victoria Barrier, the ice wall that Ross had encountered and Cherry Garrard had crossed. This was just the visible edge of a continental shelf that extended far out to sea, covered by floating ice but connected to a much larger geological system. And here's what makes Tharp's discovery so significant for understanding Antarctic exploration. She found that the barrier wasn't where explorers thought it was. The real barriers, the real boundaries in the Antarctic region, weren't the ice walls you could see. They were the underwater features you couldn't see. The continental shelf edge where the depth suddenly dropped away. The seamounts that rose like underwater islands. The trenches where ocean floor was being pulled down into the mantle. These features shaped ocean currents, which shaped ice formation, which shaped where ships could and couldn't go, which shaped the entire history of Antarctic exploration. But no one knew this during the heroic age of exploration. Scott and Shackleton and Cherry Garrard were navigating a landscape whose true structure was hidden from them. They thought of the ice shelf as a barrier to be crossed, an obstacle to be overcome. They didn't realize they were standing on top of a dynamic system, a place where ice and rock and water interacted in ways that would take decades to understand. Tharp's maps, when they were finally published in full form in 1977, changed how scientists understood not just the ocean floor, but the entire planet. The mid-ocean ridge system was where new crust was being created. The trenches were where old crust was being destroyed, pulled back down into the mantle. Continents didn't plow through the ocean floor like icebreakers through pack ice, as Wegener had imagined. Instead, they rode on plates, sections of the Earth's crust and upper mantle that moved as whole units, driven by convection currents in the mantle below. Antarctica, in this new understanding, wasn't just sitting at the South Pole by accident. It was there because of the arrangement of plate boundaries around it, the spreading ridges that encircled it, the subduction zones that shaped the Pacific side of the continent, and it had been in different positions in the past. The fossil evidence that Scott's party had died carrying made sense now, because Antarctica had once been connected to South America, Africa, India, and Australia in a supercontinent called Gondwana. It had been positioned much farther north in a climate that could support forests and reptiles. But here's what history overlooks about Tharp's work. She did it without computers. Every cross-section was drawn by hand. Every correlation between different ship tracks was done by eye, by placing drafting paper over light tables and tracing patterns. She developed techniques for visualizing three-dimensional topography from two-dimensional profiles that wouldn't be formally codified in computer graphics until decades later. And she did it while being told, repeatedly, that her interpretations were wrong. That she was seeing patterns that weren't there. That she should just draft what she was told to draft and leave the science to the men. The gender dynamics of this story are relevant because they reveal something about how knowledge gets made, how barriers get crossed. Tharp couldn't go on research cruises, couldn't collect her own data, couldn't present her findings at many scientific conferences, but she could draft. She could plot. She could see patterns in data that others missed because they expected the ocean floor to be boring, to be flat, to be unworthy of detailed attention. Her exclusion from the masculine world of ocean-going research forced her to focus on the data itself, on the tedious work of accurately representing what the numbers showed rather than what theory predicted they should show. This is a different kind of crossing, a different kind of barrier penetration than the physical journeys we've been discussing. Tharp crossed an intellectual barrier, the belief that the Earth was static and unchanging. She did it not by going to Antarctica or sailing to remote oceans, but by sitting at a desk in New York and plotting lines on paper, day after day, for years. But there's another connection here, another way in which Tharp's work relates to Antarctic exploration. Because just as Cherry Garrard and his companions had walked across the Ross ice shelf in darkness, navigating by compass and dead reckoning, Tharp was mapping a landscape she couldn't see, that no one could see, using indirect measurements and careful inference. Both journeys required a kind of faith. Faith that the compass was accurate, faith that the echo soundings were reliable, faith that human beings could understand landscapes that were fundamentally hostile to human presence. And both journeys revealed the same basic truth. The barriers that seem most imposing, most absolute, are often just the visible edges of systems we don't yet understand. The ice wall wasn't the edge of the world. It was the edge of a continental shelf, shaped by geological processes operating over millions of years. The featureless ocean wasn't empty space. It was a landscape as varied and dynamic as any on land, but hidden under water, revealed only by patient, tedious work. You might think about this as you drift towards sleep. How many barriers are real, and how many are just the limits of our current understanding? How many walls have we built in our minds? Walls that seem solid and absolute, but which would dissolve if we had better tools, better data, better maps. But Tharp's story doesn't end with maps. It ends with something stranger, something that brings us back to Antarctica and to the question of what lies beyond the ice wall. In 1977, the same year Tharp's complete map of the ocean floor was published, scientists made a discovery in the waters off the Galapagos Islands that changed our understanding of where life could exist. They found hydrothermal vents, underwater hot springs where superheated water, rich in minerals and chemicals, poured out of the seafloor. And surrounding these vents, in water that was pitch black, under pressure that would crush a human being at depths where no one thought complex life could survive, they found entire ecosystems. There were tube worms 8 feet long, clams the size of dinner plates, crabs, shrimp, bacteria, all living in conditions that seemed impossible. These vent ecosystems didn't depend on sunlight. They didn't depend on photosynthesis. They derived their energy from chemicals in the hot water, from the Earth's internal heat, rather than the sun's external radiation. It was life based on a completely different energy source, thriving in an environment that seemed as inhospitable as the Antarctic plateau Cherry Garrard had crossed in winter. And here's where the story comes full circle. Hydrothermal vents exist along the mid-ocean ridge system, along the rift valley that Tharp had discovered. They exist where new oceanic crust is being created, where seawater seeps down through cracks in the rocks, gets heated by magma below, and then erupts back out, carrying dissolved minerals and chemicals. The mid-ocean ridge system that encircles Antarctica, that Tharp had spent 20 years mapping, is dotted with these vents, these outposts of impossible life. No one had looked for these vents in Antarctic waters during the heroic age of exploration. The technology didn't exist. The conceptual framework didn't exist. The idea that complex life could exist in permanent darkness, under crushing pressure, in waters near freezing, fed by the Earth's internal chemistry rather than the sun's light. This idea would have seemed like science fiction to Cherry Garrard or Scott or Shackleton. But it's real. And it exists beyond the ice wall, in the waters surrounding Antarctica, in places that are still being explored and mapped today. The landscape that Marie Tharp revealed, the landscape hidden under the ocean, turned out to be not just geologically dynamic, but biologically rich in ways no one had imagined. So what did explorers find when they crossed Antarctica's ice wall? They found a frozen continent, yes. They found evidence of past climates, fossilized proof that Antarctica had once been warm. But they also found, eventually, evidence of a living system that didn't depend on warmth or light. A system that thrived in conditions that seemed absolutely inimical to life. They found that the barriers we build in our minds, the idea that life needs sunlight, that it needs moderate temperatures, that it needs conditions similar to those we evolved in, these barriers were wrong. This is what lies beyond the ice wall. Not a hidden paradise, not a warm valley, not a secret civilization, but something stranger and more significant than any Victorian theorist imagined. Beyond the ice wall is a world that works according to different rules, a world that reveals the inadequacy of our assumptions about what's possible and what's not. And this, perhaps, is the real significance of Antarctic exploration, the real reason why people kept crossing that barrier despite the suffering and danger it entailed. They weren't just exploring a continent. They were exploring the limits of what's possible, pushing against our assumptions about where life can exist, how the Earth works, what we think we know. But there's one more crossing to discuss, one more journey beyond the ice wall that reveals something different again. The connection between Marie Tharp's maps and actual Antarctic exploration became concrete in an unexpected way in the early 1960s. By this point, the heroic age of Antarctic exploration was over. Scott and Shackleton were dead. Cherry Garrard had published his memoir and retreated into bitter obscurity. The continent was no longer unknown. Multiple nations had established permanent research stations. The International Geophysical Year of 1957-58 had coordinated unprecedented scientific study of the region. An aircraft had made it possible to survey vast areas that would have taken months to cross on foot. But the ocean around Antarctica remained largely mysterious. Ships could traverse it, yes, but the seafloor was still unmapped in most areas. And this mattered more than you might think, because understanding the ocean floor around Antarctica was crucial to understanding the continent itself. How it formed, how it related to other continents, how it influenced ocean circulation and global climate. In 1962, a research vessel called Eltanen began systematic surveys of the Southern Ocean. The ship was purpose-built for Antarctic research, with reinforced hull, powerful engines, and enough fuel and provisions to spend months at sea. It carried echo-sounding equipment, but also dredges for collecting samples from the seafloor, and cameras for photographing it. The mission was to create the kind of detailed maps of the Antarctic ocean floor that Tharp had created for the Atlantic and Indian Oceans. The Eltanen surveys would eventually contribute data to Tharp's mapping project. But more immediately, they produced their own surprises. On one of the early cruises, the ship's dredge brought up rocks from a depth of 2 miles, rocks that showed clear signs of having been above water in the relatively recent past. Geological recent, meaning within the last few million years. This suggested that parts of the Antarctic seafloor had been elevated, had perhaps been islands or even connected to the continent, before sinking to their current depths. This finding supported the theory of continental drift, now becoming accepted as plate tectonics. Antarctica hadn't always been where it was. It had been part of Gondwana, had broken away as the supercontinent fragmented, and had drifted to its current position over tens of millions of years. The ocean floor around it had formed and reformed, had risen and fallen, as plates moved and collided and spread apart. But there was something else in the Eltanin data, something that wouldn't be understood for another decade. The echo soundings showed that the seafloor south of the Antarctic convergence, the zone where cold Antarctic water meets warmer water from the north, was unusually rough, with more seamounts and ridges than the seafloor at similar depths elsewhere. Initially, scientists assumed this was just random variation, the kind of local geological complexity you'd expect in any region. What they eventually realized was that the roughness wasn't random. It was the signature of the Antarctic circumpolar current, the massive current that flows from west to east around Antarctica, uninterrupted by any continent. This current, driven by the prevailing westerly winds, is the largest ocean current on Earth by volume. It connects the Atlantic, Pacific, and Indian Oceans, and it plays a crucial role in global ocean circulation and climate. The current's interaction with the seafloor creates turbulence, mixing deep water with surface water, bringing nutrients up from the depths and driving one of the planet's most productive marine ecosystems. The Antarctic circumpolar current is, in effect, an invisible barrier, not a physical wall like the Ross Ice Shelf, but a dynamic boundary that separates the cold waters around Antarctica from the warmer waters to the north. And this boundary, this oceanic barrier, has shaped the continent's climate, its ice sheets, its biology. But you can't see this boundary from the surface. You can't map it by sailing across it or walking across it. You can only understand it by mapping the seafloor, by tracking water temperatures and salinity, by measuring currents over years and decades. It's a barrier that exists in 4 dimensions. 3 spatial dimensions plus time, constantly shifting and flowing but maintaining its essential structure. Marie Tharp never got to see the complete mapping of the Antarctic seafloor. That work continued for decades after her 1977 World Ocean Floor Map, continues still today with satellite altimetry and autonomous underwater vehicles collecting data in areas too dangerous or too remote for ships to survey. But her contribution was foundational. She established the methods for visualizing underwater topography. She proved that the ocean floor was worth mapping in detail, that it wasn't just empty space, but a complex landscape with its own mountains, valleys, and plains. And she did it through a different kind of endurance than the physical endurance required for Antarctic sledging. She endured the tedium of plotting thousands of individual profiles. She endured the dismissal of her findings by colleagues who couldn't believe that a woman, working at a drafting table, could make fundamental discoveries about Earth's structure. She endured the frustration of not being able to go to sea herself, of always working with secondhand data, never getting to see the places she was mapping. There's a particular kind of heroism in this, though it's not the kind that gets commemorated with statues or expedition names. It's the heroism of showing up to work every day and doing careful, precise, boring work that slowly accumulates into something significant. It's the same kind of heroism, really, that Cherry Garrard displayed on his winter journey. Not dramatic rescue or last-minute salvation, but the simple persistence of putting one foot in front of the other, day after day, even when the task seems pointless. Because here's something worth considering as you settle into sleep. Most barriers aren't crossed in single heroic moments. They're crossed through accumulated effort, through countless small acts of persistence that individually seem insignificant, but collectively change what's possible. Scott's expedition didn't reach the South Pole because of one brilliant navigational decision or one moment of inspired courage. They reached it because they got up every morning, broke camp, pulled their sledges, and covered their assigned mileage, day after day after day, until they got there. And then they did the same thing, trying to get back, until they couldn't anymore. Tharp's maps didn't emerge from a single flash of insight. They emerged from years of drafting, plotting, comparing, refining. From work that must have seemed, on any given Tuesday, utterly mundane and insignificant. Plot this profile. Check this measurement. Correlate this feature with that one. Cross-reference this ship track with previous tracks in the area. Repeat tomorrow, and the day after, and the day after that. This is how barriers actually fall. Not through sudden dramatic breakthroughs, though those make better stories, but through patient accumulation of knowledge, through the willingness to do boring work carefully and well, through persistence in the face of dismissal and doubt. The Antarctic seafloor mapping that followed Tharp's initial work revealed something else worth noting. The waters around Antarctica are deeper than expected in some places, shallower in others, and the pattern of depths doesn't match what you'd predict from the continent's visible geography. There are deep trenches where you'd expect shallow shelves. There are shallow areas far from the continent where you'd expect abyssal depths. This complexity suggests a complicated history of plate movements, ice sheet advances and retreats, and changes in sea level that have repeatedly redefined where the edge of Antarctica actually is. The ice wall that Ross encountered, that seemed so permanent and absolute, is actually temporary. During ice ages, when more water is locked up in glaciers, sea level drops and the ice shelf extends farther out over what's now ocean. During warm periods, sea level rises and the ice shelf shrinks back. The edge of Antarctica is constantly moving, on timescales of thousands to tens of thousands of years. This means that when Cherry Garrard walked across the Ross Ice Shelf in 1911, he was walking on something that wouldn't exist in the same form a few thousand years later. Not that it would melt, though with climate change, that's now a real possibility, but that it would advance or retreat, thicken or thin, crack and reform in response to changes in snowfall, temperature, and ocean currents. He was crossing a barrier that was itself in motion, though moving too slowly for human perception. There's something profound in this. Something about the impermanence of the things we think of as permanent. The instability of the barriers we think of as fixed. But there's also something more immediate and practical. It means that the maps explorers used, the charts they relied on, were always slightly wrong. The coastline had moved since the last survey. The ice shelf had advanced or retreated. Crevasses had opened or closed. Navigation in Antarctica wasn't just difficult because of the extreme conditions. It was difficult because the landscape itself was unreliable, constantly changing in ways both subtle and dramatic. Modern satellite mapping has helped with this. We can now track the movement of ice sheets and ice shelves in near real time, can identify crevasse fields from space, can measure the thickness of ice using radar. But this technology was unavailable during the heroic age of exploration. Explorers had to rely on visual observation, on compass bearings, on dead reckoning. They had to trust that the landscape they'd mapped on the way out would still be recognizable on the way back. Sometimes it wasn't. Shackleton's Endurance was crushed by ice in 1915 in an area of the Weddell Sea that had been open water just a year earlier. The ice hadn't formed gradually. It had blown in on wind and current, pack ice from further east, blocking what had been a clear passage. The ship was trapped not because Shackleton made a navigational error, but because the ocean itself had changed, had become solid in a matter of days. This unpredictability, this fundamental unreliability of the Antarctic environment, is part of what makes exploration. They're so different from exploration in other parts of the world. In a tropical rainforest, the terrain is difficult, but it's stable. The river you cross today will be in the same place tomorrow. The mountain you navigate around will still be there next week. In Antarctica, the terrain can change overnight. A calm bay can become choked with ice. A stable ice bridge over a crevasse can collapse. A glacier that's been slowly flowing can suddenly surge forward miles in a matter of days. Marie Tharp's maps, showing the underlying geology, provided a kind of stability that the ice could never provide. The seafloor doesn't move on human timescales, or even on the timescales of civilizations. The mid-ocean ridge system that Tharp mapped has been there for millions of years, will be there for millions more. This underlying structure shapes where currents flow, which shapes where ice forms, which shapes the visible landscape. But the relationship between structure and surface is complex, mediated by ocean and atmosphere in ways that are still being understood. The Eltonin surveys, and the many surveys that followed, gradually filled in the gaps in Tharp's maps, added detail to the Antarctic regions that had been only sparsely sampled. And with each new cruise, each new data set, the picture became more complete, but also more complex. Features that looked like simple ridges turned out to be volcanic chains. Areas that looked flat turned out to be pockmarked with pits and scarps. The seafloor around Antarctica, far from being the featureless plain that early oceanographers expected, turned out to be as varied and complex as any landscape on Earth. But describing this complexity, making it comprehensible to people who would never see it, required new ways of visualizing and communicating. Tharp's original technique, drawing profiles at exaggerated vertical scale, then interpolating between them to create continuous maps, worked well for the Atlantic and Indian Oceans where ship tracks were relatively dense. But in the Southern Ocean, where ice and storms limited ship access, tracks were sparse, and interpolation was uncertain. Scientists began using shaded relief maps, showing the seafloor as if lit by a low sun, casting shadows that made the topography visible. They used color coding to show depth, warmer colors for shallows, cooler colors for depths. They created three-dimensional computer models that could be rotated and viewed from different angles. Each technique revealed different features, emphasized different aspects of the landscape. This proliferation of visualization techniques is worth noting because it reveals something about the nature of barriers and their crossing. The physical barrier of the ice wall could be crossed by walking across it, though it required extreme endurance. The intellectual barrier of understanding the ocean floor required different tools, different approaches, different ways of seeing. And each new way of seeing revealed features that previous methods had missed. What lies beyond Antarctica's ice wall, then, depends on how you look. If you look with echo soundings and create profiles, you see the vertical relief, the mountains and valleys. If you look with gravity measurements from satellites, you see density variations that hint at the structure of the crust below the sediment. If you look with magnetic measurements, you see the patterns of magnetic polarity frozen into the rocks, recording the history of the Earth's magnetic field as new ocean floor formed. If you look with cameras, you see the small-scale texture, the individual rocks and organisms that cover the seafloor. Each way of looking crosses the barrier in a different way, reveals a different aspect of what lies beyond. And this suggests that barriers aren't single things, they're multiple, overlapping, each requiring different tools and techniques to penetrate. The physical ice wall, the intellectual barrier of ignorance, the technological barrier of inadequate instruments, the social barrier of who's allowed to do the exploring and mapping. All of these exist simultaneously. All of them have to be crossed to fully understand what's there. Tharp crossed several of these barriers, though not all. She crossed the intellectual barrier by recognizing the significance of the Rift Valley in her profiles. She crossed the technological barrier by developing better ways to visualize seafloor topography. But she couldn't cross the social barrier that kept women off research vessels, couldn't collect her own data, couldn't see firsthand the places she was mapping. Yet her work was fundamental to our current understanding of the ocean floor, and by extension, of plate tectonics, of the Earth as a dynamic system rather than a static one. The maps she created are still used today, updated with new data, but retaining the fundamental structure and visualization techniques she developed. As you drift towards sleep, you might consider this. Sometimes the most important exploration doesn't involve going anywhere. Sometimes it involves sitting still, looking carefully at data, seeing patterns that others miss because they're looking for the wrong things. Sometimes crossing a barrier means realizing it isn't where you thought it was, that the real obstacle is in how you're thinking about the problem, rather than in the physical world itself. But there's one more aspect of Tharp's work that connects to the question of what lies beyond Antarctica's ice wall. One more discovery that emerged from decades of patient mapping. In 1985, 8 years after Marie Tharp's complete map of the world ocean floor was published, scientists using data from the Eltanin surveys made a discovery that connected Antarctic seafloor mapping directly to the history of life on Earth. They found, in sediment cores taken from the ocean floor south of Tasmania, a sudden change in the types of fossils present. Below a certain layer, dating to about 34 million years ago, there were fossils of organisms that live in relatively warm water. Above that layer, only fossils of cold water organisms. This transition was sharp, occurring over a period of perhaps a few 100,000 years, a blink of an eye in geological time, and it marked the point when Antarctica froze. Before this transition, Antarctica had been cold, but not ice-covered. It had supported tundra vegetation, possibly some scrubby forests and sheltered areas. After this transition, it was the frozen continent we know today, covered by ice sheets miles thick in places. What caused this dramatic change? The answer, it turned out, was visible in Tharp's maps, though she hadn't realized the significance at the time. The mid-ocean ridge system south of Australia, part of the continuous ridge that encircled Antarctica, had been slowly spreading, pushing Australia northward and opening the gap between Antarctica and the last continent to which it had been connected. Once this gap was wide enough, the Antarctic circumpolar current could form, isolating Antarctica thermally from warmer waters to the north. The current acted like a barrier, but in the opposite direction from the ice wall. Instead of keeping explorers out, it kept warmth out. Antarctic waters, no longer mixing with warmer waters from the north, cooled dramatically. And once they cooled below a critical threshold, ice began to accumulate. Snow fell and didn't melt. Year after year, century after century, millennium after millennium, the ice built up. Within a few 100,000 years, a relatively brief period, Antarctica transformed from a cold but habitable continent to the frozen wilderness that Cherry Garrard would struggle across 33 million years later. This discovery illustrates something important about barriers and what lies beyond them. The ice wall isn't just a physical feature. It's the visible manifestation of a planetary scale system. A system involving ocean currents, atmospheric circulation, ice sheet dynamics, and geological processes operating over millions of years. When Ross encountered the Victoria Barrier in 1841, When Cherry Garrard crossed the Ross Ice Shelf in 1911, they were interacting with the endpoint of this system, the place where all these processes become visible as ice and snow. But they had no way of knowing this. The conceptual framework didn't exist. Continental drift wasn't yet accepted. Ocean circulation patterns weren't well understood. The history of Antarctica's glaciation wasn't known. They were exploring a landscape without understanding the processes that created it, like trying to understand a book by reading only the last page. Marie Tharp's maps, and the work that built on them, provided context. They showed that Antarctica wasn't just sitting at the South Pole by accident or divine design. It was there because of specific geological processes: the breakup of Gondwana, the spreading of the ocean floor, the opening of the gaps between continents that allowed the Antarctic circumpolar current to form, and these processes had consequences that rippled through the entire Earth system. The formation of the Antarctic ice sheets changed global sea level, dropping it by hundreds of feet as water became locked up in ice. This changed coastlines around the world, created land bridges between previously separate continents, altered ocean circulation patterns. The ice sheets reflected sunlight back into space, cooling the planet. The cooling changed atmospheric circulation, altered weather patterns, affected ecosystems thousands of miles from Antarctica. In other words, the barrier that the ice wall represented wasn't just a local phenomenon. It was part of a global system. Crossing that barrier, understanding what lay beyond it, required understanding processes operating at scales that individual explorers, standing on the ice with their sledges and their frozen sleeping bags, couldn't possibly perceive. This is perhaps the most significant finding to emerge from a century of Antarctic exploration and mapping: that local barriers are embedded in global systems, that you can't fully understand one without understanding the other. The ice wall exists because of the Antarctic circumpolar current. The current exists because of the configuration of continents and ocean basins. That configuration exists because of plate tectonics. Plate tectonics exist because of convection in the Earth's mantle driven by radioactive decay in the core. Its barriers all the way down, or rather, its barriers embedded in systems embedded in larger systems. And each level of system requires different tools to explore, different techniques to map. You can cross the ice wall on foot. Cherry Garrard proved that. But you can't understand why it's there without ships taking echo soundings, without satellites measuring gravity and magnetic fields, without drill cores sampling sediment and ice, without decades of patient data collection and analysis. This might seem like an abstract point, but it has practical implications. In the 21st century, as climate change begins to affect Antarctic ice sheets, the question of what lies beyond the ice wall takes on new urgency. If the ice sheets shrink, if the ice shelves collapse, what will be revealed? What will the landscape look like? How will it affect sea level, ocean circulation, global climate? These aren't hypothetical questions. Antarctic ice is already changing. The Larsen B ice shelf, which had been stable for at least 10,000 years, collapsed in 2002 over the course of just a few weeks. Other ice shelves are thinning, developing new crevasses, showing signs of instability. The West Antarctic ice sheet, which sits on bedrock that's below sea level, is particularly vulnerable. If it melts, global sea level could rise by more than 10 feet. Understanding these changes, predicting what might happen, requires the kind of detailed mapping that Tharp pioneered, extended now to the ice itself. Scientists use ice-penetrating radar to map the bedrock beneath the ice sheets, discovering mountains and valleys that haven't seen sunlight for millions of years. They use satellites to track the movement of ice, measuring velocities down to fractions of an inch per year. They drill cores through ice miles thick, analyzing air bubbles trapped in the ice to reconstruct past climates. This is exploration of a different kind than what Cherry Garrard did, but it serves a similar purpose: to understand what's there, to map the unknown, to push beyond the barriers that limit our knowledge. The difference is that now the barriers aren't just physical. They're conceptual, technological, computational. How do you model ice sheet dynamics when the physics is complex and the data is sparse? How do you predict the behavior of a system that has multiple stable states and might flip between them in ways that aren't linear or gradual? These are the questions that current Antarctic research grapples with, and they're direct descendants of the questions that drove earlier exploration. What lies beyond the ice wall? Not in the sense of physical geography, we've mapped that pretty thoroughly, but in the sense of understanding, of knowledge, of being able to predict what will happen as the system changes. Marie Tharp died in 2006, having seen her work go from dismissed as girl talk to recognized as foundational to Earth science. She was awarded the Hubbard Medal by the National Geographic Society in 1978, the first woman to receive that honor. Her maps were used in textbooks, in documentaries, in countless scientific papers. The seafloor landscape that she'd revealed through patient, tedious work had become part of the basic knowledge that every Earth scientist learned. But she never went to sea. She never saw the places she'd mapped. She never stood on the deck of a ship and watched the echo sounder trace out the profile of an underwater mountain or valley. Her exploration was entirely vicarious, entirely mediated through data collected by others. Yet it was no less real, no less significant than the physical exploration carried out by people who went there. This suggests something about the nature of barriers and their crossing that might not be immediately obvious. Physical presence isn't always necessary for understanding. Sometimes the view from a distance, the ability to see patterns across wide areas, reveals things that close-up examination misses. Tharp could see the entire mid-ocean ridge system because she wasn't on a ship traversing a small section of it. She could recognize the Rift Valley running down the center because she was comparing profiles from across the whole Atlantic, not just looking at one profile in isolation. Similarly, understanding Antarctica, really understanding it, not just surviving crossing it, requires distance, perspective, the ability to see it as part of a larger system. Cherry Garrard's winter journey to Cape Crozier was an extraordinary achievement of physical endurance. But it didn't reveal why emperor penguins bred in winter, or why Antarctica was frozen, or how the continent related to the rest of the planet. Those understandings came later, from people who assembled data from many sources, who looked at the big picture rather than the immediate struggle of the next mile. This isn't to diminish the importance of physical exploration. Someone has to collect the data, has to go to the difficult places and take the measurements. The echo soundings that Tharp plotted had to be collected by ships going to sea, by crews enduring storms and cold and months away from home. The samples that revealed Antarctica's glaciation history had to be collected by research vessels working in dangerous waters. The ice cores had to be drilled by people living in field camps in some of the harshest conditions on Earth. But the understanding comes from synthesis, from putting all these pieces together, from seeing the patterns that emerge when you look at enough data from enough places over enough time. It comes from the boring, patient work of plotting and mapping and analyzing. Work that doesn't make for dramatic stories, but which is absolutely essential to actually knowing what lies beyond the ice wall. As you slip into sleep, consider this final thought about barriers and exploration. The most important discoveries often don't feel like discoveries at the time. They feel like routine work, like just another day at the office, like plotting yet another profile or pulling a sledge yet another mile. It's only later, when someone looks at the accumulated work and sees the pattern, that the significance becomes clear. Cherry Garrard couldn't know that his journey would become famous as the worst journey in the world. Tharp couldn't know that her Rift Valley would help overturn fundamental assumptions about how the Earth works. They just did their work, day after day, as carefully and thoroughly as they could. And eventually, the work revealed something about the world that no one had known before. That's what lies beyond the ice wall. Not a destination you reach in a moment of triumph, but a slowly accumulating understanding built from countless small observations, each insignificant in itself, but collectively transformative. The exploration of Antarctica continues. New instruments, new techniques, new questions drive ongoing research. But the pattern established by Cherry Garrard and Tharp remains the same. Patient persistence in the face of difficulty, careful attention to detail, willingness to do boring work well, and the understanding that real discovery is usually a slow process rather than a sudden revelation. These qualities cross barriers more reliably than heroism or genius, and they reveal what actually lies beyond. Not fantasy or speculation, but the complex, interconnected reality of how our planet works.